Hi, this is Mr. Swanson, and today we're going to go over our newest unit on stoichiometry. And so the first lesson, 7.1, is just an introduction to the basic ideas in stoichiometry. And if you want, you can follow along in the online textbooks, 9.1 to 9.2. And there are so many good videos online about stoichiometry too. So this is just kind of some of the basics, but you can find out a lot more information by just Googling stoichiometry and watching some of those YouTube videos. In this stoichiometry unit, we're going to focus on chemical reactions and measuring how many grams of something do we start with in a chemical reaction, and then how many grams should we get out of that chemical reaction of a given product. And so we're going to be focusing on chemical reactions and going from start to finish and doing some measurements throughout the process. Now, without thinking about it, you've gone through the process of stoichiometry before, because you're essentially doing that every time you cook. And so when you're cooking, sometimes they tell you an amount of something like 2 graham crackers and 1 marshmallow, but sometimes they tell you grams too when you get into a more sophisticated recipe. And so one question we could ask you is, if you wanted to make 4 s'mores, how many graham crackers do you need? And so what we're going to be doing is we're going to be looking at these ratios between 1 s'more, you need 2 cracker squares, okay, or 2 graham crackers. And so you're going to think about this ratio when we're doing stoichiometry. Another way to do it is, if you had 6 chocolate squares, you want to know how many s'mores you can make. So in this case, we would look at, we have 3 chocolate squares, and for every 3 chocolate squares, we can make 1 s'more. And so if we start with 6, how many can we make in 2? Well, this is an easy example because we're dealing with nice whole numbers, but we're going to be getting into grams and moles, and so we're going to have to follow a very specific process. So I'm going to apply dimensional analysis, which is an idea that we looked at last unit, and try to answer this very basic question with a chemical reaction, which is very similar to what we just talked about. And so here, the first one, we want to make 5 molecules of CO. How many molecules of oxygen do we need? Well, if our goal, the known value that we're trying to get to is 5 molecules, and it's going to be super, super important to write CO2. Okay, not just 5 molecules, but 5 molecules of carbon dioxide. How many molecules of oxygen are we going to need? And so we're going to have to get rid of molecules of carbon dioxide, so we're going to have to put molecules of carbon dioxide at the bottom. And we want to figure out molecules of oxygen. And so here is the first time we're actually using this mole ratio, that for every 1 molecule of carbon dioxide, because that's the coefficient here, we need 2 molecules of oxygen. And so when we finally do this, molecules of carbon dioxide cancel out. 5 times 2 divided by 1 is 10 molecules of oxygen. Okay. So see if you can do problem number 2 and come back, and I will give you the answer to it. So hopefully you were able to get 6 molecules as the answer, and 6 molecules of water is technically a better answer. Now, if you're wondering in the question, why are they saying unlimited oxygen, that's really important, and that's going to come into play a little bit more at the end of the unit. But for now, what that is just telling you is, don't focus on the oxygen, just focus on the methane. Here's what it would look like with the s'mores example. And the key part of this that we're showing you is it doesn't matter what things you're comparing. You could compare 2 reactants together. You could say, if I have 2 graham cracker squares, how many marshmallows do I need? Or you could say, if I had 9 marshmallows. How many s'mores can I make? You can compare reactants to products, products to reactants, and so forth. And you compare two types of reactants or two types of products if they have it. And then briefly, here's what it would look like then if we were using the mole ratio for an actual reaction. A 1 over 2, 2 over 1. It doesn't matter which way you say it. However, we're going to just set the 1 on top according to the dimensional analysis that you're solving in the problem. So when it's going to be important which one you put on the top or bottom based on which one you're trying to cancel out. So it's probably best right now for you to just see if you can understand what we were just saying and try one of these problems on your own, just converting from moles of one type of thing to moles of another thing. Please use the dimensional analysis and keep it organized because these are very simple problems and they will get much, much harder. So pause the video and come back after you've tried it on your own. So hopefully you got these answers, and I do want to draw your attention to one little thing. In this answer, I did this in a fraction, so that's fine. I just didn't want to bother putting it into my calculator, but here I put it into the calculator, and I put the answer down as 1.2, even though it was really 1.16 repeating. Why did I round it to 1.2? Well, keep in mind that this has 2 sig figs, and I'm doing multiplication and division, so my answer should have 2 sig figs. Now, these right here, this 1 to 3 ratio, would be considered kind of like the counting unit. It's a very specific defined ratio that's not based off of a measurement, so that doesn't get counted in the amount of sig figs. Now, hopefully you understand how to go from a mole of something to a mole of something else. And that's going to be very, very important because in a chemical reaction, you make something new. And so you need to be able to make that conversion. However, moles aren't super practical because you can't really weigh out a mole. And so we're going to have to actually start with a mass rather than starting with a mole. So now we're going to add in another step where, let's say we're given 100 grams of oxygen, how many grams of CH4 am I going to need? So this is going to make this a multi-step process, but that's what we're going to practice right now. So we're going to actually have to do 3 conversions in this process, but the process is always going to be the same, and no conversion is actually hard, so all it requires is a good setup and, kind of nice handwriting if you can, but just keeping everything organized. So the first thing we're going to do is go from grams of oxygen to moles of oxygen because we can only relate 2 different substances together with a mole ratio. Then we're going to use that mole ratio from the balanced chemical reaction. And finally, we're going to convert back into grams of methane because we want something practical in the end. So this entire process could be broken down into 3 steps where in the very top, we show you that you can go from one to another, and then you can just keep going and getting the answer. But I'm showing you down below, down here, that instead you can kind of make it one big long railroad track of conversions. And so as you're going through, you're going to be like, okay, grams of oxygen, cancel with grams of oxygen, mole of oxygen, cancel with mole of oxygen, mole of methane, cancel with mole of methane, and we're left with what we want to find in the end, grams of methane. And to do that, all we did were conversions of molar mass, mole ratios, and molar mass, which are all things you've done before. So hopefully by now you've realized that nothing that we're doing is difficult, but it just involves putting a bunch of steps together and keeping it organized. So I would recommend screenshotting this and saving it and using it as we're learning this process and going back to say, okay, what was I given? Okay, got to turn it into moles. Okay, and do that first step. So I was given something. Always convert it into moles because it's only through the mole ratio that we can actually go into moles of something else. Whether it's a product you want to know how much you're going to make or how much of another reactant you're going to use. And then finally, we want to go into usually grams, or it could be liters of gas. It just depends on what we want to find. So I don't need to do another problem here, but this is the problem we solved in just a couple slides ago. So you might want to go back to see now, if you can understand each of the 3 steps that we did for the process. What's really nice about this is there's a clear, concrete answer at the end. And so for some people, that makes it really nice because this is math, this is algebra that we can really understand and comprehend. As soon as we get it, I think a lot of people will think this is maybe fun is a stretch, but it's very doable. So why don't you stop and try this problem and then come back and check your answer. Okay, so here are the steps kind of shown in order, showed also to in green where I was canceling out the units, and then the answer of 48.6, which is rounded to 3 sig figs, and it's rounded to 3 sig figs because there's 3 sig figs. So the answer should have 3 sig figs. So the next couple of problems are just some practice problems where you're going through the same procedure for each of the problems. So in each example, I'll pause it, give you some time to do some practice, and then I'll show you the answer. And if you need any help during any of these steps, or you're like, why did I do this? Screenshot your specific problem, send me a message on Schoology, or just talk about it in class the next day. And I'd love to go through kind of how we went from one step to another. So try this problem on your own. Keep in mind, we started with 3 sig figs, so we want to end with 3 sig figs. Here's another problem for you to try, so just pause the video and come back when you're done to check your answers. In this case, we're going to be looking for liters of H2, and you're going to want to remember that 1.0000 moles equals 22.40 liters of gas at standard temperature and pressure. Now, when you're reading the question, just be very careful to take a look at what you're given to start off with. So in this case, we didn't start off with any grams or liters. The first step was already done for us, so we were already in moles of one thing. So the second step was to then convert into moles of another thing, and then that third thing was, okay, moles isn't practical, but we can measure liters, so let's convert it into liters, and that gets us our final answer right here. So it's just one less step, and so don't forget to read through the question very carefully. Now in this problem, remember that 1 mole also equals a certain amount of particles. Now we're not going to use this one as much, but it's still important that we go through the exercise where you can see how to do it. And so pause the video and come back when you are completed. It's really crucial in this unit to make sure every time you write a number down, you always have the unit and then what substance it is. So every time I write a number down, there's a unit and then whatever that substance is. And that's going to make it really easy to spot your own mistakes, check your answers, and for me to give you full credit on a problem where if you make one little error, the answer is going to be wrong, but you can still get the majority of the points. Here's a problem where we didn't give you the balanced chemical reaction, and in some of the labs you might need to write out a balanced chemical reaction, but our goal is to focus on the stoichiometry part of it. So first start by trying to write out the balanced reaction, and then go through the next 2 slides and try to solve the problems, and come back and I have some more answers for you when you're done. So a couple key points when checking your answer. Number 1, again, rounded to 2 sig figs. A lot of times when people solve a problem like this, you're going to see them write another 2 right here. Because, they're like, okay, the 2 is in the chemical reaction, so I'm going to put that 2 here. And that's not true because, well, I mean, that is true, but this last step is a molar mass conversion. Remember that in this step, right here, these 2 things have to be equal to be considered a conversion factor. And we know 2 moles of aluminum is not 26.98. Instead, only 1 mole is that. So make sure you don't get stuck with putting that 2 a second time. You've already accounted for the ratio of a 2. Okay, and here are the final worked out solutions. Now in this example, I want to show you how in one problem, and this is going to happen a lot, you got to calculate the molar mass for something. You might use that again later. So again, this is why if you keep everything organized, you're gonna have to do less work. Now remember, all the answers need to be a number, a unit, and what are we talking about. For every single problem, this is how we want to see your work. Hopefully this made sense. We're gonna have lots more time to practice, and come to class with questions.